Hello class 10. The topic that we are going to discuss today, as you see written on the board, is electrical energy and power. Now energy, power and of course work, these are topics that you already know about. You've studied about these topics specifically in chapter 2. Now we are going to discuss about exactly the same thing. It's exactly the same thing but in terms of electricity. So we are going to talk about the amount of electrical energy consumed, okay, how much is the work done to take a certain charge from one point to the other, and of course we are going to talk about the electrical power, so to say, consumed in a particular electrical circuit, okay, and the different power ratings and voltage ratings that are given in any electrical device that we use. Do you remember? Any kind of an electrical device, it be that we are using, be it your cell phone charger, your smartphone charger, be it the television, be it the refrigerator or an electric bulb, tube light, whatever kind of an electrical device it be, any device will have its power rating given and it will also have something called a voltage rating given, but we'll talk about that later. First of all, let us talk about energy or work done, because mind you, energy and work done are basically one and the same thing. They are one and the same thing, so to say. So, say we have a charge at this point, let's say point A, and we have to take this charge to point B. So the charge is Q, say capital Q is the charge that we have at point A, and we want to take this charge to point B. Now, in order to take this charge Q from point A to point B, there has to be some work done. Alright? If we have a bag, say for example, and we want to take that bag from one point to the other, obviously we have to do work. We have to carry that bag and we have to lift it up, of course, okay, and then we have to take it to that certain point. Likewise, to take a charge from one point to the other, there needs to be work done. Okay? And the work done will be equal to the amount of charge that is to be taken, which in this case is Q, into the potential difference between these 2 points. Because we have learned from the definition of potential difference itself that the potential difference between these 2 points is the work done to take a unit charge. If Q is the work that is done, if Q is the work that is done, what am I saying? I'm sorry, okay? If the work done to take Q amount of charge is W, only my statement was wrong. The work done to take Q amount of charge is W. So the work done to take 1 or unit amount of charge will be W by Q. And of course, this is what is called the potential difference between these 2 points. Okay, so from the definition of potential difference itself, therefore we get to see that the work done to take charge Q from point A to point B is W, which is equal to Q into V. Now, from the definition of current, we know current is charge divided by time, or current is the rate of flow of charge, how much charge is flowing in a certain time. So from here, we can write Q is I into T. Okay, so we replace that thing over here. So W is, therefore I can write I V T. Okay, so this is another expression for work done to take a charge Q from one point to the other. Now specifically, if in between these 2 points, in between points A and B, we have a certain resistor, or so to say, there is certain resistance offered to the flow of this charge Q when we take it from point A to point B. Okay, so there is some resistance offered, and the resistance offered is R, say for example. Okay, so in this electrical circuit now we have a resistor. Now if we have a resistor, or if the Q charge experiences certain resistance, then from Ohm's law we know V can also be written as I into R. Now Ohm's law specifically valid for a resistive circuit, mind you, do not forget that. Okay, so this is from Ohm's law, we know. Ohm's law. Okay, so instead of V, what I can write is I into R, and therefore I can write W is I squared RT. Okay, this is one of the expression for work done. Now I could also have written I in terms of V and R from Ohm's law. So I will be V divided by R. So I can substitute for I. Okay, so this is V by R into Vt. So this is V squared by R into T. So this is another expression for work done. So generally, what are the expressions that we can write for work done is, one is this VIT or IVT, whatever you prefer writing. The other is I squared RT. Sorry, not plus. The other is V squared by R into T. So these, if you want to add this also, you can add W is Q into V. Okay, but these are the most basic and important relations for work done that you need to know. Okay, based on these three. So these are three different equations that I'm writing. W is VIT is one expression for work done. W is I squared RT is another. And W is V squared by R into T. Okay, so based on these equations, you might take numericals also. Okay, so very, very important relations for you all. Now, since work done is also the same as energy, since work done and energy are one and the same, so we can also say that the energy consumed in a certain electrical circuit, whatever kind of an electrical circuit it be, in a certain electrical circuit is given by VIT, I squared RT or V squared by R into T. Okay, so that is the amount of energy consumed in a certain electrical circuit, or the work done to take a charge from one point to the other. Okay, class 10. So if you wish to, you can pause the video and copy this. I suggest you all to copy this. Okay, so let me erase this now. So let's talk about the unit of work done now. Unit or units of work done. Okay, so this will be the unit of work done or also that of electrical energy. Okay, so the unit, as we already know, the SI unit is joule for both energy and work done. Alright, there are other units also. Watt second and joule are one and the same thing, because watt second we get from the definition of power actually. Okay, we are going to talk about power, but let me just show you the definition for power. Power is defined as the rate of doing work. Okay, so work is measured in joule, time is measured in second. So joule per second is what is called watt, the SI unit of power, remember. Okay, so work or energy therefore can be written as watt into second. So joule is watt into second. Alright, so the third unit could be watt hour. These are bigger units. Fourth is your kilowatt hour. This is kilowatt hour. What I'm writing here, I'm basically writing the units for electrical energy, remember. Although work and electrical energy is one and the same, okay, but basically these units are spoken about with regard to your electrical energy. Okay, so in fact, these are very, very important units, especially watt hour and kilowatt hour. These are also called the commercial unit of electrical energy. Especially kilowatt hour and watt hour. Alright, so these are the units for electrical energy. Okay, watt second, watt hour, kilowatt hour are units used specifically with respect to electrical energy, not with respect to work. Remember, work is basically measured in joule. Alright? So do remember this. And what is important for you all is to find out the relation between kilowatt hour and joule, watt hour and joule. It's very, very important for you all. Okay, sometimes you get 2 marks question asking you to find the relation between kilowatt hour and joule, or for that matter, the relation between watt hour and joule. Let me show you the relation between kilowatt hour and joule in here. The relation between watt hour and joule, you can try finding it yourself. Okay? So do remember these relations, very, very important. Very, very, extremely, very important. Let me keep this for now and let me erase these parts. Alright, commercial unit of electrical energy. Alright, so 1 kilowatt hour, by the way, is also written as small k, capital W, small h, kilowatt hour. Likewise, watt hour is written as capital W, small h, like this, watt hour. So 1 kilowatt hour can be written as 1000 watt hour, because kilo means 1000. This can be written as 1000 watts into 1 hour, of course. Now 1 hour is 60 seconds into 60 seconds. Very, very easy, okay? So 60 into 60 is 3600. So 3600 and 3 more zeros. So 3600 and 3 more zeros. This many watt second. But watt second is what is called joule, remember. So this can be written as 36 into 10 to the power 5 joules also you can write. Or you can also write 3.6 into 10 to the power 6. Okay. So you can write 36 into 10 to the power 5 joules. Or you can simply write 1 kilowatt hour. You can also write it this way. 3.6 into 10 to the power 6 joules. So this is the relation between kilowatt hour and joule. Okay, many times this has been asked to find the relation between kilowatt hour and joule. Now watt hour you can find from here itself. You just have to remove this kilo, or so to say, you just have to remove 3 zeros. Alright, so when you remove 3 zeros, the relation between watt hour and joule will be 3.6 into 10 to the power 3 joules. That is the relation between watt hour and joule. You can try finding that yourself. Okay, now let us discuss electrical power. I hope I can erase these. So let me erase. So let's talk about power, or rather electrical power. Now from the definition of power itself, if P is the power, power is the rate at which you can say electrical power is the rate at which electrical energy is consumed in a circuit. It is the rate at which electrical energy is consumed in a circuit. Alright? So because work done and energy are one and the same thing, do not forget. So that is, okay, let me write for you. It is the rate at which electrical energy is consumed in a circuit. Is consumed in a circuit. An electrical circuit also you can write. That will be more specific. In an electrical circuit. It is the rate at which electrical energy is consumed in an electrical circuit, of course. So that is the definition of power. Now, when we substitute these values of work done over here, what do we get? We get power is VIT divided by T. So this will be power is V into I. From here, I squared RT, work done divided by T will give us I squared R. Likewise, V squared by capital R into T divided by this T will give us V squared by R. So these are the different expressions for power consumed in an electrical circuit. Okay? So from the definition of electrical energy or from the definition of work done itself, we get that being divided by time, of course, we get the expression for power. Now again I repeat, this expression, power is V into I, is true for any kind of electrical circuit. Because any electrical circuit will have a certain potential difference and there will be certain current flowing through it. But these two are specifically for a resistive electrical circuit, remember. Alright? So these are the expressions for power, and talking about, so I believe I can erase this part. Talking about unit of power it's the same that you've already studied. Unit of power is watt. Okay, this is what is generally used in, when we talk about electrical power. Okay, so with regard to electrical power, the most basic unit of power that is used is watt. Of course, there are other units of power also. Kilowatt, this is one. Okay, we have kilowatt. This is also sometimes used in with regard to, so to say, electrical power. Okay, you have horsepower. Horsepower is not used in case of electrical power consumption. These are the basic units that are used. Okay, but of course power has other units also, do not forget. We have horsepower, capital H, capital P, and what is the relation? This is equal to how many watts? 746 capital W. Capital W is watt, remember. Okay, so these are the things about electrical energy and power. Thank you.